We're diving into what might be the biggest roadblock in AI development right now. And it's not really about intelligence itself, it's about the cost. Welcome to the deep dive. Today, we're tackling this paradox with large language models. The better they get, the bigger they need to be. And that means the costs just keep spiraling upwards.
It's exactly right. Scaling up, whether it's adding parameters or making them generate long chain of thought outputs, it's becoming incredibly resource intensive.
Yeah, to the point where only a few huge companies can really play at the cutting edge.
Precisely. And that's why efficiency is moving from a nice to have to an absolute necessity. We need smarter solutions to get out of this scaling trap.
So what's the alternative?
Well, the core idea we're digging into today is a technique called retrofitting recurrence.
Retrofitting recurrence. Okay, sounds pretty technical, like model mechanics.
It is a bit like model mechanics, yeah. But the underlying concept is actually quite elegant. It's this emerging approach, a different way of thinking about scaling that cleverly decouples how much computation you do from the actual size of the model.
Decouples compute from size.
How? You'd essentially get to run more calculations, make the model think harder, without physically making the model bigger or needing more memory for that extra thought process.
Okay, that almost sounds too good to be true. So our mission for this deep dive is to figure out how researchers actually achieve this. You're saying they take existing models like Tiny Llama, Olmo, even the Big Llama models.
Yep, established pre-trained models.
And they perform, what do they call it? Model surgery to turn them into these recurrent, parameter-efficient versions.
That's the term they use, yeah, model surgery.
Well, before we scrub in for surgery, let's nail down the main goal here. S-time compute scaling. What exactly does that mean, and why is it better than just, making the model write more stuff out, like in chain of thought?
Okay, so test time compute scaling means using more computation during inference when the model is actually generating an answer to get a better result, but without just making it type out more tokens.
Right, because that chain of thought approach, while useful, it feels kind of indirect.
It is, and it can be wasteful. Think about forcing the model to verbalize every little step, token by token. It's slow, it increases the context length, which eats up memory.
So you hit limits pretty quickly. Memory limits, processing limits.
Exactly. Depth recurrence offers a way around that. You get a better results on benchmarks without needing more unique parameters in the model and without needing to do more pre-training from scratch.
How? By looping. You mentioned looping.
Yes, by looping. You reuse a block of the existing parameters multiple times. And crucially, doing more loops, increasing the compute, doesn't increase the model's memory footprint or the context size during that inference step.
Ah, I see. So the extra thinking happens internally.
Precisely. It allows for potentially more complex reasoning to happen within the model's latent space, its internal representation where the information bandwidth is much higher.
Okay, that makes sense. It's like doing the math in your head quickly versus writing every single step down slowly.
That's a great analogy.
Yeah.
You're not forced to translate complex internal states into relatively low bandwidth tokens just to keep track of the reasoning.
All right, so let's get into the surgery itself. How do you actually take a standard transformer, which runs layers sequentially one after the other, and make a part of it loop back on itself?
The key enabling factor is something fundamental to the transformer architecture itself: the residual stream.
The residual stream. Okay, break that down for us.
Think of it like a shared workspace or a digital whiteboard that gets passed along through the layers. Each layer reads what's on the whiteboard, adds its own contribution, the residual update, and then passes the updated whiteboard to the next layer.
And because all layers use this same whiteboard format.
Exactly. They all operate in this shared representation space.
No.
The size and shape of the data stays consistent. That consistency is what makes it possible to take the output from a block of layers and feed it right back into the input of that same block for another pass.
So you're not adding new layers for depth, you're just reusing a chunk of the existing ones.
Definitely.
Okay, what are the specific new parts they introduce in this retrofitted architecture? You mentioned P, R, and C.
Right. So first you have the prelude. These are typically the early layers from the original model, including the initial embeddings. They handle the first look at the input.
Like reading the prompt.
Exactly. Then comes the core component, the recurrent block. This is the block of layers that gets looped, iterated upon. This is where the intensive, deeper computation happens.
The thinking part.
The thinking part, yeah. And finally, you have the coda C. These are the final layers, including the part that converts the internal representation back into tokens, the embeddings. This happens only after the very last loop of the recurrent block.
Okay, prelude in, recurrent block loops, coda out. Seems logical. But wait, If the recurrent block output feeds back into itself, how does the original input information from the prelude keep influencing the later loops?
Ah, good question. That's where another piece comes in. The linear adapter. This is really important.
What does it do?
After each loop of the recurrent block, you have the state that just finished. You also still have the initial processed input from the prelude. The linear adapter's job is to combine these two things.
So it merges what I just thought with the original question.
Basically, yes. It takes the prelude output and the previous recurrent state, concatenates them, which temporarily doubles the width of the data pathway, say, from $.
Okay, so it gets wider for a moment.
Right. Then the linear adapter applies a learned transformation to map the combined $2 representation back down to the standard model with dollars. It intelligently merges the information before the next loop starts, ensuring the context is updated without permanently increasing the model size.
Okay, that makes sense. It's like a smart junction point. Now, you also mentioned something counterintuitive. They actually removed layers from the original model during the surgery. Doesn't that hurt performance?
It sounds like it would, right? But they found that being selective was key. They didn't just keep all the layers. They experimented and found that, for example, using earlier layers for the prelude and later layers for the recurrent block and coda worked best.
So they cherry-pick the layers.
Pretty much. In one configuration they detailed, using Tiny Llama, they actually discarded 6 layers entirely. The resulting recurrent model used only about 73% of the original parameters.
73%. And it still worked well.
Better, in fact, on the target tasks after retraining. It suggests that how you use the parameters and allowing them to be used repeatedly via recurrence can be more important than just having more unique parameters. Sometimes less, used more effectively, is more.
Fascinating. Okay, so the architecture is leaner, but capable of deeper processing through loops. But training, this must be computationally expensive, right? Even with fewer parameters, running those loops over and over during training takes time and energy. How did they tackle the training efficiency?
Yeah, training efficiency is critical. They measured it in FLOPs, floating point operations, basically the amount of raw computation. They hit 2 major efficiency wins here. First, pre-trained initialization.
Meaning they didn't start training the recurrent model from random noise?
Absolutely not. That would take forever. They took the weights from the existing pre-trained model like Llama and used those as the starting point for the parameters in the prelude, recurrent block, and coda.
And that gives them a huge advantage.
Massive. They estimated, based on the learning curves, that starting from random weights would have required something like 950 billion additional training tokens to reach the same performance level as the model initialized from pre-trained Llama weights.
Wow. Nearly 1 trillion tokens saved just by initializing smartly. Okay, that's a huge saving. What was the second efficiency gain?
The second one was about managing the recurrence itself during training, recurrence scheduling. You can't just tell the model on day 1, okay, now do 32 loops for every example.
Why not? Too much compute.
Too much compute. And it's likely unstable early on. So they used a curriculum approach. They started training with maybe just 1 or 2 loops on average, and then gradually, systematically increased the average number of recurrent iterations throughout the training process.
Like easing the model into deeper thought patterns.
Exactly. Using schedules like a linear increase or a specific one-scored function help them get better performance improvements for the amount of FLOPs spent during training. It's about making the training process itself efficient in terms of computational effort.
Makes sense. Train smarter, not just harder.
Right. And they also found that using a specific optimizer called muon worked better than the standard AtomW for these recurrent models. It led to lower loss and more stable training, which again contributes to overall efficiency.
Okay, so the model surgery is clever, the training is efficient. Let's get to the results. Does this actually lead to better reasoning, especially on tasks where that deep thought should really pay off?
Yes, that's where it shines. They focus particularly on reasoning-heavy tasks like mathematics. They retrofitted models like Tiny Llama, Olmo, and Llama, then fine-tuned them on math datasets like Nemotron CC Math.
And the results?
On benchmarks like GSM-8K and Math, the depth-recurrent versions consistently outperformed their non-recurrent parent models, especially when you compare models trained with the same computational budget, the same number of FLOPs.
So for the same training effort, recurrence gives you better math skills.
That's what they found. And the real advantage became clear at inference time. When they allowed the recurrent models to actually use more compute by running more loops, say up to 32 recurrence iterations,
They pulled ahead even further.
significantly. The llama conversions, for instance, showed really strong gains on these math problems when allowed to recurse 32 times compared to the baseline fixed depth model. It demonstrated that the architecture can effectively use that extra test time compute.
Okay, but earlier you mentioned they removed layers. Did that cause any problems? Like, did the models forget how to do basic language tasks because parts of their brain were removed?
That's a really important point.
Yeah.
Yes, the initial surgery, the layer removal, could degrade general language modeling capabilities. They needed a way to heal the model after the operation.
Heal the model?
They used a two-phase training procedure. First, after initializing and setting up the recurrent structure, they did a healing phase where they trained the model briefly on general web data, just to restore its broad language understanding.
Okay, like a refresher course.
Exactly. Then, after that healing phase, they moved on to the task-specific fine-tuning, like the math data.
And did the healing work?
It did. They saw, for example, about a 5% increase in accuracy on a general knowledge benchmark called ARC challenge after the healing phase, compared to without it. So this two-step process allowed the recurrent models to regain general confidence while still excelling on the specialized math tasks, even with fewer unique parameters overall.
That really ties it all together. It's a very thoughtful process. So the big takeaway seems to be that retrofitting recurrence is genuinely efficient. It gives you parameter savings and this flexible compute scaling at test time.
Yeah, it offers a path to potentially better reasoning without just building ever larger models. It decouples those concerns in a really useful way. They figured out how to make the existing architecture work harder, smarter.
Which leads us to a really interesting final thought for you, the listener, to mull over. They've shown how to efficiently create and train these recurrent models, but the paper hints at the next frontier, native adaptivity.
Right. Can we build models that learn to decide for themselves how many recurrence loops they need for a given problem?
Exactly. Could a model look at a question, recognize its difficulty? Oh, this is a complex geometry proof, versus this is a simple factual recall, and then dynamically allocate the right amount of compute, the right number of loops.
It's almost like asking if we can teach an LLM a form of metacognition to know when it needs to think deeper.
That capability, that self-aware allocation of computational effort based on task difficulty, that feels like a major step towards truly flexible and efficient intelligence. Teaching models to know when to think harder, that's a fascinating challenge.
Absolutely. It opens up a whole new area of research into efficient adaptive reasoning in these latent spaces.
Definitely something to keep an eye on. If you want to explore the architectural details or that healing process more, do check out the source material. Thanks for joining us on the deep dive.
See you next time.